Newton form for interpolation, right? Newton form for interpolation. So this goes back to the idea that I emphasize a lot before we talk about the rule finding, right? The bisection and so on. Is the idea of iteration, right? Iteration. It's really powerful idea. The powerful philosophy is that you do it iterate by iterate. You not only do you make things better and better as you iterate, but also you can use your previous iterates. You're not wasting your computation or your effort before, right? Philosophically, of course, every scheme is different. So what I will talk about here is that if I'm going to use INF, right? This is a degree n polynomial interpolating f of x, a general function of f of x, right? A non-polynomial function f of x. You find n plus 1 points, you get a degree n polynomial. Okay, again, there's a mismatch 1 there, right? Degree n polynomial. I'm going to use a subscript n to denote the degree n. Okay. But we don't go to degree. In some cases, for example, in some real world situation, you have data come in bit by bit, the so-called data stream, right? So you have more and more data, and the incoming new data should be understood on top of the old data, right? Maybe a lot of the telescope observation, for example. There are many such cases. You have a so-called data stream. So you basically get more and more xn. Xn, you get xn plus 1. Maybe you need to change your interpolating polynomial, right? So that it can interpolate at one more point that just came in. Okay? Does that make sense? I mean, that's just a little motivation, right? The background math is the following. So we're asking ourselves, right? So this guy is degree n, right? Degree n. We're asking ourselves, hey, if I already have a previous guy that I worked really hard to get, right? I sub n minus 1 is a degree n minus 1, right? So this is n minus 1's degree. Okay, and now I have this xn, right? Can I build on top of my previous result? Okay, can I do this? Right. So of course the goal is that this guy interpolates f, some unknown function. In the real world, you don't really know the function. That's why you need to approximate it. You approximate your data by a polynomial. Your previous result interpolate this unknown function at is a degree n minus 1. So it's x0 to x sub n minus 1. All right. Now you have a new xn. Is there anything I can do so that I can fix my previous interpolant? Right? This is the idea. I mean, if you understand the idea, and I certainly forgot about the formula. What's that something equal to? There's a formula for that. But if you understand the idea, you can derive it very quickly. Right? So that this interpolates f of x at one more point. We have those points that we just wrote down, xn plus 1. But get one more point, xn. Right? That will be great, right? That will be great. It will be great because we're not wasting our previous calculations. Does that make sense? There are a few things to think about, right? This something this something should be a degree what? So it must be degree n. Okay? And the second requirement is that this something this is the function of x, right? Function of x. So we're coming out with functions, right? If you plug in this something again, this is just notation. You can change into something else, right? This if you plug in the I xi, if I is less than or equal to n minus 1, this guy should be equal to what? Remember, let me give you a hint, right? Remember, we have already the I sub n minus 1f. This is a polynomial, right? This is our degree n minus 1 interpolating polynomial. This guy, if you evaluate at those xi, because it interpolates at those spots, so those are equal to the yi, right? Equal to the y, your data. That's what the interpolation means. And the left-hand side, I sub n, the new polynomial that we're trying to figure out. And one more point, okay? You should continue to interpolate at those points. You don't want to ruin what you did already, basically. Right? So those should be also equal to yi. It's still interpolating polynomial. These two means that if I plug that xi into the remaining term, it should be equal to what? So 0. Again, you don't want to ruin the job you did already, right? You interpolated the temperatures okay, well, for the previous 15 days. The new contribution for the previous days should be 0. You don't want to change the previous 15 days temperature. All right? So, and this something of xi, right, is a degree n polynomial. We know that. It's a degree n. Must be degree n. And we also know how many roots there. If you plug in xi, get 0. That means those are the roots. It's roots. How many roots do we get? N, exactly. x0, x1, all the way to xn minus 1. Right? This is 0 for I equal to 0, 1, all the way to n minus 1. There are n roots. This tells us we already know the form. We already know this function. This something of x, the something that you add, you append. Once you know a root, you know a factor, as we were talking last time, right? I know x minus x0 is a factor. And I know x minus x1 is a factor, all the way to x minus xm minus 1. They're all factors, otherwise they're not zeros, they're not roots. Of course, you can multiply this by any constant. I'm going to denote a sub m by a sub n, a constant, because you get 0 multiplied by constant is still 0, right? So to be general, it should be constant multiplied with those product of factors. Okay? That's how we get this extra, how we figure out what should we add. It's degree n, and you know the n roots. Then you're done. Of course, we're not quite done yet, right? The only thing to figure out is what is this an? What is this an? What is this an? Okay? What is this an? And there's one condition we haven't used it yet. What's the condition? You have this extra point. You have 1 day temperature. At day 16, you get a temperature 85. like today, that we haven't used at all, right? You plug in xn, you should get yn. That's you plug in xn, which is the new polynomial, right? If you plug in xn, you should get your new data yn. The newest data points in your data stream. Okay, this shows that what's that? My yn, I basically plug in xn into the equality above, that we figured yi plus equal to y plus 0, the same equality. So I should get yn is equal to my old polynomial, my previous polynomial, evaluated at this new day, which is, if I were to use my old polynomial from the 15 days of temperature, I can evaluate today by plugging 16. I will get a temperature. It's just like it's modeled by it's guessed by the model, right? You plug xn, and then plus this guy, an times xn minus x0 all the way to xn minus 1, right? I just plug xn into that equality, which give us a way to solve for an. You solve for it, all right? So this is what? Yn minus n minus 1 f. Your existing polynomial evaluate at the new data points, locations. Your yn is a data, the data. Divided by, let me use this pi notation. I is from 0 to n minus 1. Your xn minus xi, right? Xn minus xi. Okay. So there you go. You'll get this form, right? You know exactly what is that equal to, right? So we ended up having a nice formula, in f of x, right? This should be equal to n minus 1 f of x plus this an, all right? This an plus this an plus this guy times that x minus x0, x minus x1, x minus x n minus 1, right? Okay, that's it. That's called Newton form, the iterative, the way you can do interpolation in an iterative fashion. There's one little thing that's missing. All right. We need, for iterative scheme, we need an initial. You need to start it, right? In that bisection, all those things, we need an initial guess, the secant chord and so on and so forth, right? So here we need a starting guy, which is what this I0 f is. For the I0 f is equal to what, right? Recall In means degree n. It's x0 to xn, degree n. I0 means degree 0, right? Degree 0. So it's a constant, right? It's a constant. So at this moment, when we talk about I0, the first point, 1 day, 1 day's temperature, right? If you were to use, you have 1 point, so you have this 1 point, x0, and you have the value y0. That's the easiest interpolation. You have 1 point, and you want to come up with a degree 0 polynomial, which is a constant, a horizontal line, not just straight line. It's a horizontal line. If it's not horizontal, it's a linear function. Horizontal line. If you want to use horizontal line to approximate this one point, that horizontal line should pass through it. Yeah, yeah. This function, right? This function. So this means my first guy is just equal to f. Is just equal to that y0, right? The data y0. Or if you have a function, if you are actually given a function that you need to interpolate, for the temperature, we'll talk about we're not given function, we just have the data, so it's y0. If you have a non-polynomial function, for whatever reason, you need to approximate it by polynomial, then evaluate the function at that one point, right? Get a constant. Y0 is a function, just constant. Give me any x, I give you the same constant, okay? Then that would make the whole the scheme complete. You have a starting point, you have an iterative. You give me I0, I know how to go to I1. You give me I1, I know how to go to I2, right? In fact, we should do it, right? Like you can see. So if you have of course, for this guy, we defined, what is it? So here, so this is actually the an. We have name for this, right? That's all omega, right? Omega that we defined last time. Omega n plus 1 is up to n plus xn. So here is only omega n x, right? Which is this guy. Just replace that constant times omega n x. All right. So if we actually do it, right? So you have maybe this your x0. That's your x1. So you have x0, x1, right? x0, x1, and your first you only have 1 point. Your first guy is just function like that, right? F of x0, or you read the data from your reading, whatever. And now you have 2 points. What's going on if you just use a formula, right? I1 of f of x is equal to that I0, right? That's that I0. So it's y0, that, right? That's y0, that's y1. So it's our I0 plus look at that constant, right? That an we just found out. It's yn is 1, so it's y1 minus the evaluation at the new point, which is still y0, right? Still y0. It was a constant function. So the evaluation at the new x1 is still y0 divided by now n is 1, so I from 0 to n minus 1 is I from 0 to 0, just one guy. So the new point x1 minus all the previous points, only had 1 point, x1 minus x0 times it's x minus x0, right? X is changing, you get a function. What is this? It should look suspiciously familiar to you. The point from pre-calculus, right? The point slope form, right? That's how you write down a linear function. You get a point, it passes through this point, and you get a slope. Okay, get slope. No? You want one more point x2 over here, right? What it does is that it takes this guy, right? Of course, this gets more and more complicated without actual numbers. but it takes this guy, and there will be a nice formula later, right? It takes this existing guy, right, plus you have your new yn, right? Y2 minus this one is not as straightforward as a second point, right? But what you can see is that you're adding a quadratic term there. So here is constant. You evaluate the previous guy at x2, right? Which is y2 minus y0 plus y1 minus y0 divided by x1 minus x0 times this new x2 minus x0, right? Divided by, now n is 2, right? So you're going to get x2 minus x0 times x2 minus x1. And this whole thing multiplied with x minus x0 times x minus x1. You see that? It turns out that we can prove the following, right? If we define, so if we define this guy, right, this guy, this is equal to f at the last endpoints minus the first endpoints over the very last point minus the very first point. And of course we define, if you only have one point, you're going to get your function evaluated at that point, or like we have been doing, just y0, right? These guys can be your y0. So then the an that we just proved, right? This an, this is a1, right? And this guy is your a2. Okay, that an is actually nothing but this guy. Then this an is actually equal to f a0, x0 to xn. Okay. That's it's nice in the sense that if you can do a few steps, you see, right? You do let's do a few steps. So the idea is the following. Let's keep the previous example. All right. So you have your x0, x1, x2, right? x1, x2, right? And f at one point is equal to that one point, right? By definition, it's a trivial start, and then we follow the iteration, right? So that gives us I0, right? I0 f. If you only have x0 of x, this is a constant function, the same as before, all right? Same as above. If you have 2 points, right? So the formula tells us that, again, there's a little bit of algebra. I1x should be equal to your previous guy plus this constant, which is denoted by you have one more point, x1, x0, x1, right? Times this omega 1, which is x minus x0. That's a new way of writing our an. That's the only change. The omega n stays the same. I'm just copying down all those things, right? So now you just need to compute this coefficient. It's a constant coefficient. which gets messier as you saw, right? Gets messier. But by using this formula, it's easy. See, f. So by the iteration, this f x0 x1 this is equal to the last. If you remove the beginning, remove the first point, which is x0, you keep x1, minus you remove the last point, divided by the last point minus the first point, right? By the formula. So that's equal to y1 minus y0 divided by x1 minus x0. That's the same as above as well, right? The slope. So this is correct. And you start to appreciate the power when it goes to next term, even more term, right? And also on computer, it's quite easy to code up. I mean, that one is also easy to code up, but this one is probably even easier, right? So you're going to have your f x1 x2 minus f x0 x1, right? Remove this first point and then remove the last point, divided by x2 minus x0, right? Each of those is defined iteratively as well, and for one of those we already have it, right? So the y1 minus y0 divided by x1, this guy is y1 minus y0 divided by x1 minus x0, right? The other guy is f x1 x2, which is by same definition is y2 minus y1 divided by x2 minus x1. This whole thing divided by x2 minus x0. So that this is equal to that guy. All right.